have some matrix multiplying a certain vector, which turns out to be equivalent to that vector, just multiplied by some number. Okay, and we are rather familiar with this situation in linear algebra, because in linear algebra, such a vector is called the eigenvector. And such a value is called the eigenvalue. Okay, so all of a sudden, the problem of solving a two-level quantum mechanics reduces to the problem of solving a 2x2 matrix diagonalization problem, which I think we are all familiar with. Okay, so well, then let me just proceed with the solution. So I'm going to absorb the B0 into this factor called energy by a simple redefinition, and then by virtue of this redefinition, the two-level Schrödinger equation problem becomes simply that of diagonalizing this sort of 2x2 matrix. Okay. Okay. Well, this b dot sigma, if you just write it out explicitly, is going to be this. Okay. Well, probably you have enough recollection left from your classes in linear algebra to recall the process by which you solve such a problem. But actually, I want you to forget forget your background. In linear algebra, and start absorbing start learning new ways. Okay. And I kind of like to impose this new way of solving this two-level problem, not only because it's more convenient, but that's not the only reason why I want to impose this new method. Actually, the deeper reason why I want to do that is because it's connected to a kind of a deep notion of a Bloch sphere. This notion plays a very important role in the way we think about quantum computation and how the quantum state, the two-level quantum state, evolves over time. And the method I'm going to show you from now has a most explicit connection to the idea of a Bloch sphere. Okay, so that's why I want you to forget about the old ways and learn the new ways. Okay, so here's the new ways. So since B is just an ordinary three-dimensional vector, I can decompose that vector in terms of its magnitude and some unit vector. And this unit vector has a spherical coordinate representation: sine theta, cosine phi, sine theta, sine phi, and cosine theta. Okay, so this spherical coordinate representation comes from this angle. It's called the polar angle. And so this is my unit vector. And if I take the projection of the unit vector into the xy plane, xy plane, then the angle that you measure from the x-axis toward that projection is the azimuthal angle, phi. Okay, so using the polar angle and the azimuthal angle, you can express the this orientational vector or the unit vector like this. Okay, so this is something that you got to learn probably in the calculus class, and that knowledge will come into play in a very useful way. Okay, so now thanks to this sort of a spherical decomposition of my B vector, so now actually I want to write everything in the same page. So let me erase some parts to make space. So now using this spherical representation, I can write my Hermitian 2x2 Hermitian matrix by first taking out the amplitude part, B, and then B3 is just cosine theta, and then B1 plus IB2 from these combining these two numbers will be equal to some phase times sine theta. And the other off diagonal is, of course, the complex conjugate of that. And finally, this element will be a minus cosine theta. Okay. So this multiplying my my vector will be energy multiplying my vector again. But then since B is some positive number, you can always divide both sides by B like that. And then maybe E over B I can call epsilon. Okay, and then the whole problem reduces to that of finding or solving the eigenvalue problem given in this form. Okay, so now you can sort of start forgetting everything else. What should I erase? Yeah. And try to see if I can solve this problem. Right? So now I have taken out everything else. Okay, so now the trick is to try to find alpha and beta in terms of these two angles. Okay, I mean, that would be the most natural thing anyhow. And that can be done. Yeah, that can be done. And you can check that, first of all, there are only two eigenvalues, +1 or -1. And if you choose the +1 eigenvalue, then the corresponding eigenvector is cosine half theta E of I phi sine of half theta. So this appearance of the half angle is maybe slightly uncomfortable, but actually there's nothing wrong about it. I suppose it's just a matter of getting used to. And secondly, if you choose the other eigenvalue, then the corresponding eigenvector is sine of half theta. And this would be E of I phi cosine half theta, but there is a minus sign over here. Okay, so let me make some space so that the minus sign will be more transparent. Okay, so now let me express this this eigenstate with this symbol plus, and I'm gonna use this other symbol to express the other eigenstate. Now, according to the theory of matrix diagonalization and so on, these two eigenstates are going to be orthogonal to each other. Okay, which means that if I take the inner product of the minus eigenstate with the plus eigenstate, the result would have to be 0. Okay, so I'm going to check that. First, I multiply their first elements respectively, which will give me cosine half theta, sine half theta, plus, now I'm going to take a complex conjugate of this element and multiply that with this element. So if I take the complex conjugate of this, then it's minus E of minus I phi cosine half theta. And then I'll just borrow this expression over here. And taking the multiplication and through and finishing up the addition, we'll find a 0. Okay, and maybe it's also worthwhile to check that they are already properly normalized to unity. Okay, so yeah, I think this is it. So now the nice thing about it is that you don't have to go through this matrix diagonalization process every time you encounter such a problem, because these two formulas for the two eigenstates of the two-level problem are simple enough that you can almost commit these expressions to memory. Memorize, yeah. Yeah, if you stare at these expressions long enough, you will kind of see, how these expressions flow, and it will start to make more and more sense to you and so on. Well, anyway, so yeah, so this is it. This is the way you solve the two-level problem. Okay. So just to make the story complete, I give you some. Maybe this is just like a summary of what I said in this particular video. I give you this two-level problem. Then I transform it into a time-independent problem consisting of this form. Okay, So by dividing out the b from both sides, I end up with the epsilon as the eigenvalue. And there are two eigenvalues, plus and minus 1. And there are two eigenstates, plus state and the minus state, whose forms were given in the previous page. And restoring time dependence, then, I find that there are two eigensolutions to this problem, which is, well, it's it will be that, and the other one would be that. Okay. So these are the two independent but time-dependent solutions of the Schrödinger equation for a two-level system. Okay, and the structure of these two eigenstates, plus and minus, is completely dictated by the elements of the Hamiltonian. Remember those thetas and phis? Well, these thetas and phis are determined by the choice of the Hamiltonian, element in the Hamiltonian, which in turn fixes the two angles theta and phi, which in turn fixes the explicit forms of these two eigenstates, plus and minus. As you can see, this is the plus eigenstate and this is the minus eigenstate. And if you know what the theta and phi are, then you know what these eigenstates are. Okay. So yeah, I guess that's it. Yeah. So I claim that that's everything you need to know about the recipe for solving the two-level problem. And yeah, one more thing. Yeah, that's worth mentioning is that once you have these, sorry, maybe I should mention it here. Yeah, once you have this, then you can talk about the probability that this plus eigenstate be found in the zero basis state. Okay, so the probability is the this overlap squared, absolute value of the overlap squared, but then that's nothing but this quantity being squared. Okay, so that's a cosine of half theta squared. Okay, and now similarly, the probability that this this eigenstate psi plus be found in the basis state 1 is going to be the absolute value square of this, right? So that's going to be sine half theta squared. But if you apply the rules of trigonometry, then this comes out to be 1/2 times 1 plus cosine theta. The other one turns out to be 1/2 times 1 minus cosine theta. So quite nicely, the sum of these probabilities become exactly 1. Okay, and what was cosine theta again? Well, cosine theta was in fact was amplitude of the B amplitude. Well, sorry, cosine theta was B3 divided by the amplitude of B. So this is actually the 0, 0 element of the Hamiltonian divided by the actually the overall length of the elements H00 plus H01 squared. Okay, So that's how you fix the cosine theta. And this cosine theta in turn controls the probability that this eigenstate be found in the 0 basis state or the 1 basis state. Okay? Yeah, and a similar calculation for the psi minus eigenstate will give you this somewhat the reverse of this, so that this probability is now 1/2 1 minus cosine theta, and this probability is 1/2 times 1 plus cosine theta. And the reason why these probabilities are switched is because in place of cosine theta, we have a sine theta half, and in place of sine theta half, we have a cosine theta half over here. So these cosines and sines get replaced, interchanged, as you go from psi plus eigenstate to the psi minus eigenstates. Okay, yeah, I guess that's really all there is to it. So I hope you enjoy learning it.